Today, I'm going to talk about multimodal AI agents and sort of give you a little bit of overview of what we've been doing and some of the work that's been happening around that space. It's a very exciting space. I think that a lot of people are thinking that the year 2025, 2026 is going to be the year of agents. So we'll see a lot more work coming out of academia and industry in that space. So when we think about large language models, right, we think a lot of different sort of innovations that happened in the last few years. We see examples of in-context learning, zero-shot learning. You have very good representations of text. You have general, long, and coherent text that these models can generate. You have sort of world knowledge, and so amazing things has been happening in the space of large language models, right? But what I would like to talk to you about today is this notion of going beyond just the language models. So you can think of language models as, given the question, the language model can generate the answer. Instead, we can try building systems that basically can automate a lot of laborious tasks. Right. So, and a lot of productive tasks we perform today on the computer potentially, as well as many tasks that we perform on the web, could potentially be automated. Okay. So, for example, how many of you have tried setting up AWS instance? Right. My students are basically saying it's a really difficult process to do. The question is, couldn't you have an agentic model that goes and sets up AWS instance for you, right? So you can start running your experiments. Or, wouldn't it be nice, and I think the technology is getting there a little bit at this point, is, create a set of PowerPoint slides to present the content of this paper, right? So I give you the paper, the agent reads and sort of goes to the PowerPoint and organizes slides and creates and gives you sort of a presentation of the paper. Can you automate some of the tasks that we're doing on Excel, going on the web, and so forth, right? You can imagine a lot of useful outcome if you're actually able to design models that can do those tasks. In this sort of lecture, I'm going to be focusing primarily on web agents and sort of give you a little bit of overview of what these models are, how we evaluate these models. And the idea here is that, you have a basic language model, some sort of for a foundation model. Obviously, you need some form of text understanding like in HTML, and you also need to have a very good understanding of the visual information, like the actual website itself, right? So you can think of visual encoding plus some form of text understanding that goes into a large language model and that gives you some form of web grounding, right? That you can then use for performing tasks on the web. And there's been a lot of work. I'm not going to list. There's been a lot of work in the last few years where people are trying to sort of understand and trying to build systems that can do these tasks. Let me show you an example, right? An example of a system where I can say, suppose I give the task to my agent. Get me to the page of a good Thai restaurant in Pittsburgh. It should have at least 200 reviews and 4.3 stars. Pick the one with the highest rating, right? And this is what the system does, right? So it's sort of, it goes on Yelp. It sort of searches for Thai restaurant. So it types in autonomously Thai restaurant, right? It's then searching through possible restaurant in Pittsburgh. It sort of finds one of these restaurants, which has 4.5 star rating. It's a Pusadi Garden. It's actually a pretty good restaurant in Pittsburgh, right? It's a good Thai restaurant. Now it's complete. Now imagine I'm asking it to say, well, get me a reservation at this for 2 people at the earliest date and use my name, J.Y. Koch, who is the student who built this, and the phone number, right? And so the agent goes on Google, finds this particular restaurant, looks at the dates, looks at the next available date, and actually successfully making a reservation, right? And putting the phone number, and then basically stops because you need to get a confirmation to actually book something, right? So it basically says, in summary, the next action I'll perform is stop, unable to proceed without confirmation code for further instructions to complete the reservation, right? So you sort of have this notion of the agent that takes tasks, it generates chain of thoughts within thinking, and then takes the action. Or I can give the example of help me navigate to the shirt that has on it, right? So it goes on Amazon. It's trying to basically look for something similar and, finds a shirt that has something similar, right? These are the examples that are heavily cherry-picked. out of, I think that we've tried maybe like, 30 times, and out of 30 times, one of them succeeded, right? So that basically means that these systems are not really working very well at this point, but it has the potential of, give you a flavor of what these systems can do. And I think in today's world, like OpenAI's operator kind of like sort of, moving in that direction is one of the very strong models that's out there. So today I'm going to talk about three different things, right? I'm going to talk about Visual Web Arena, which is a way of evaluating multimodal agents on some of the realistic visual tasks. I'll talk about some of the inference time algorithm, what we call the research algorithm for large language model agents, which sort of allows you to potentially do interesting search, apply interesting search techniques to find necessary information on the web. And then the last part, I'll talk a little bit about some of the way of scaling up data for training these agents. Because one of the aspects of these agents in general is the availability of data. What can you do online and how can you get the data online, right? So let's look at the Visual Web Arena. One of the earlier versions was developed by folks at CMU. Right, it was done by Xuyan Zhu and Frank Zhu. They've introduced the notion of Web Arena, which is a fairly realistic environment at the moment. It has popular categories like shopping, Reddit, and GitLab, which is equivalent to Amazon and Reddit and GitHub. It's a self-hosted open source, essentially, environment, which is re-implementation of the environment. And the data comes from real websites, from Amazon, Reddit, and GitHub. And what's interesting about this environment, and I'll talk about this, the tasks are fairly easy for humans, about 78 success rate, but very difficult for language models. At the time, they've reported numbers like 14%. The only problem with this particular task is the tasks are designed to use just HTML source code, right? And we found that a lot of times whenever you're dealing with HTML and JavaScript, it's a very messy type of representation. Interactive elements that when you're interacting with the environments, they don't get displayed correctly in HTML. There is like Java, CSS code, and it's very hard to kind of like process. And in context length, HTML pages can be fairly complex. Like they can easily fill up to 100,000 tokens, right? If you're kind of like trying to look at that. So, and this is how it sort of looks like, you have this, kind of like HTML-based representation. Spatial layout is also not conveyed very well in HTML. So it looks like just a text-only representation. It's very difficult to deal with, right? Just because HTML is messy. So we've tried building what we call Visual Web Arena, which is we try to build and track the process of multimodal agents that can actually have visual grounding. So we've designed these visually grounded tasks to test the abilities of these models. And it's sort of inspired by Web Arena, so we call it Visual Web Arena. And you have visual inputs and outputs that allows you to work with unique and interesting sort of, and something that's real world. And again, we sort of have the environments of what we call one-stop shop, which is essentially Amazon-like environment, Reddit, and OS class, which is more like a Craigslist type of environment, with a class field type of environment, right? So let me show you, and then you can think about that, you have some representation, I have some visual input, and I ask you to solve something that actually requires visual grounding and visual understanding. So let me show you some examples of this. Let's say I give you the task. I ask you to find this exact bike. So I'm looking for this bike that's listed for $300, $500 and post a comment offering $10 less than the asking price. Okay. And this is what the agent has to do. Again, it's a simulator. It's a fully self-hosted environment, right? You sort of go, you navigate, you find this bike, and then you basically make a posting by offering, $10 less than what the asking price is. Right, that's just one example, right? And that basically you've completed, successfully completed that task. And I can imagine in the future there's going to be agents that's going to be bargaining on your behalf, and there's going to be agents on the other side that's going to be, making you counter offers. Here's another example. Let's say I ask you, buy the cheapest color photo printer and send it to Emily's place as shown in the image. And what you can see, this image is upside down. which makes it fairly difficult for existing models to sort of look at this and actually figure out what the address should be, right? So some of these kind of like tasks we designed so that it wouldn't be that easy for the models to solve. And so what the agent needs to do, it sort of needs to go, it needs to find, it needs to sort by price, it gets the printer, it adds to the cart, then it goes and it starts completing, the address. So, it has pull down menu. So it sort of, looks fairly realistic, right? And then you go and then you place the order. And when you end up in this state, that particular state, that basically means that you've successfully accomplished the task, right? Again, just to reemphasize, it's a simulation. It's not actually doing it on the real web. It's a self-hosted environment. Here's another one where it requires you to sort of jump between two different websites. You can ask, what's the 2022 total nominal GDP of the area that produced most sugarcane in the year of 2021 in billion, right? And that's your landing page. What's interesting here is that you're essentially asking the model to understand the images. Because if you look at the year 2021, that's over here, and you look, I think in this case, Asia produced more sugarcane than Brazil, or the other way around. Brazil produced more sugarcane than Asia. So you kind of like have to look at these graphs and understand which country you should be looking at, right? So if you kind of zoom in, you can sort of say, okay, I think that was Asia that produced more sugarcane. So you have to go on Wikipedia and then find the answer, right? And the answer is 339 trillion GDP. So you can kind of see that you have to sort of have this visual grounding. You have to understand images. You have to understand graphs to solve some of these tasks. All right. So the way that the environment is represented, we can think of this environment as a POMDP environment. So this partial observable Markov decision process. So you have states, you have actions, observations, and transition function, right? And so for those of you who've worked in reinforcement learning or who've been sort of dealing with Markov decision, MDPs, that should be familiar. And that was the goal, to design the environment in such a way that it becomes an MDP so that you can potentially, train your favorite reinforcement learning algorithms on this. So the environment itself have observations, whether it's in HTML, whether it's the visual representation, like the actual website itself, and something that we call the accessibility tree, which is a cleaned up representation of HTML. You have a set of actions, and the set of actions is actually a fairly diverse set of actions, right? You can click on particular element. You can hover over particular element. This is an interesting one. You can type in a particular element and text, right? So you can think it's not just a set of discrete actions. Basically you can type in whatever, right? If you're searching for something or you're filling certain boxes, you can have a new tab, so you can jump to a new website. You can focus on a particular tab. You can close the tab. You can go particular URL. You can go forward, go backwards, scroll up, scroll down. And then you have an action called stop and then answer. Stop is the action where the model basically says, okay, I've solved the task, stop, and then I give you the final answer. In this particular environment, you have deterministic transition function. You have the state that generates the HTML page. And given the state and an action, you generate the next state. And the next state generation is actually deterministic. Basically meaning that if you're on a particular website and you click on a particular element or you type something, there is only one, there's no stochasticity, so, gets you to the next state. And we also define the reward functions, and the reward function is primarily to evaluate when you've successfully solved a task. So it's a fairly sparse reward signal that we get in this environment. Okay, but let me walk you through what the model actually needs to do here, right? So what the model needs to do is it, has to start on the homepage. So here you're trying to find the cheapest printer. And you have to navigate to the printer category, right? In terms of the actions that you need to take. Then you have to sort by descending order. So if you click sort by price, right? Then you click on the cheapest color printer. So you have to choose what's the cheapest one. So you kind of like have to understand how much each printer costs, and you have to choose the cheapest one. Then you have to add it to the shopping cart. That's another step. You have to proceed to checkout. That's another step. Then you have to fill in the form correctly, right? With the information given to you in this image. And then you have to place the order. So if you look at the entire trajectory here, it's fairly complex trajectory, right? The model has to sort of reason about what it's seeing on the web. It has to understand what I mean by the cheapest. So it has to have a notion of sorting. Then it has to really understand good multimodal abilities to understand what I'm seeing in the images. What's the address, and I have to go in and fill in the address, right, with the right information. So if you look at it, it's not a very trivial task to accomplish, right? And that's just one of 1,000 tasks that we've designed. So in terms of the distribution of tasks across the websites, we've looked at how difficult those tasks are. I think we have 950 tasks in total, close to 1,000 tasks. And you can see about 15% are easy. Basically, what that means is that it's easy in terms of reasoning difficulty and easy in terms of visually understanding what I'm asking you. Basically means you have to do only a few clicks to actually solve the task. And then you sort of have this corner here, which is fairly difficult. Reasoning difficulty, so I really have to understand what I'm seeing in the image, and visual difficulty and reasoning difficulty basically means that I have to click on a lot of things and kind of explore to successfully accomplish this particular task, right? So in this particular environment, you can actually split and try to understand, is it my visual models I'm missing, or is it my reasoning is missing? Here's how we evaluating these in this environment. So we have execution-based evaluation. So for example, a lot of times we want to find the exact match. So if I'm asking you the question, what's the ISIN number of the company that occupies the largest portion of Warren Buffett portfolio? Then I kind of like go to Wikipedia, I find Warren Buffett portfolio, and then I sort of get the information, and I need to get this exact number. Sometimes, if I said add something like that to the man's whatever this man is wearing to my wish list, then I kind of like find something, and I basically have visual QA, like is this a polo shirt, yes or no? Is this a green shirt, and so forth, right? And then you have sometimes when you're looking for something, you say it has to include above 200 or below 30, above 20,000, below 30,000, and so forth, right? So you can kind of like have these verifiers that once I give you the final state, I can actually run these verifiers and sort of tell you, have you solved the task or not? And for a lot of these prompts, there is only one solution, right? Because the environment is not, the full internet, it's fairly constrained, but at least you can verify whether your model actually successfully solved the task or not. Now, when we think about LLMs or visual language, VLMs agents, visual language models, the way to think about this is the following, right? One thing I can do is I can look at the HTML and try to use that as a representation into my LLM. It's also cluttered with a lot of unnecessary information. It has a long and confusing context. There's been a lot of work where people sort of doing markups where they trying to identify the relevant parts of the HTML and trying to use that. There's another representation is to use something that's called set of marks, which is a simplified representations. So what it does is it basically puts bounding boxes around elements, around clickable elements, right? So whether I can click on certain elements or not, and that's something that you can get from any HTML, right? So that's set of marks representation, something that you can do. Both of these representations have advantages and disadvantages. Set of marks is useful because actually visually I understand what I'm seeing in the image and what I can click on. But it's also a very cluttered type of representation. And there is a third type of representation that people are now beginning to use, which is coordinate-based representation, where I'm just trying to predict the coordinate of where I need to click. So ultimately, it's probably going to be a combination of both HTML, set of marks, and kind of coordinate-based representation. And the way you can think about these sort of representation is that if, let's say, I have a regional web page, I can use the set of marks representation, right? So I can put the bounding boxes and have IDs for each box and sort of have some representation what each box is actually doing, and perhaps have some form of captioning of each image. So I have this sort of set of marks elements in the text as well as the actual visual representation, right? And if I'm trying to find this post, navigate to the comment section of it, then you pass it to the LLM or VLM agent, and then the agent actually executes a precise action to do next. For example, I want to click on element ID 31, and element ID 31 is one of the elements here, right? And so again, the way that we typically have a representation, I have a goal, I get an observation, I represent it using set of marks. That goes to the multimodal large language models, both the text and the image, as well as the goal. And the model generates chain of thoughts. So in this case, it would generate, let's think step by step. The objective is to navigate to the food, the post, and so forth. To navigate to this listing, I need to click on the comment linked associated with a sushi. In summary, my next action will be, I'll perform action click 34. And again, that's the action that you're clicking, right? So that's one particular action that the model is taking. And then it goes, once you click on that particular element, the simulator will go to the next web page, the next state, and then you repeat this process, right? And here again, the action is you take a particular action from the list of actions that I've mentioned before. Now, if I look at sort of baseline models and kind of try to understand which models are working well and which models are not, what's interesting is that if I only use text-only based representation, then I hit something like 9% accuracy. If I use text plus caption, so if I caption any visual information, any images that I have on the web pages, you have improvement. If I actually try to use multimodal model, you get further improvement. If I use set of marks representation, sort of like I understand clickable elements and what I can do, you get a little bit of improvement as well. So you kind of go from 9% to something like 18%. And then you get human level performance. And the human level performance hits close to, in this case, for Visual Web Arena, it was hitting something like 85, 86 accuracy, right? So there is a big gap between what people are capable of doing it and what existing models are capable of doing. This was interesting. The way that we've collected the data is we actually asked students at CMU to solve these tasks. We give them the prompts, we give them the tasks, we give them the environment, and they just interact with the environment, and then they end in the state. And then we evaluate using our execution-based evaluation whether they've successfully solved the task. What's interesting is that we found that humans were not at 100%, right? And what's interesting, a lot of mistakes that people make are kind of silly mistakes. So for example, if I ask you to find, if I ask you to say, well, find me the cheapest bicycle, right, that has these specific constraints or these conditions. I want it to be black. I want it to be of this color. I want it to be less than $2,000. Go find me the cheapest bike. What people tend to do, people tend to kind of like go through the simulator. They find one bike, they find a second bike, and then they basically say, okay, I'm tired of looking for anything else, right? So I have two bicycles, I take the cheapest one and say I'm done. Whereas actually there are 10 bicycles, right, that satisfy the constraint. So people are just not very good at information seeking tasks. Or at least we didn't pay students enough. We gave them pizza to kind of like go and spend more than a few minutes to solve these tasks. So majority of the kind of information seeking tasks is where people were not really good at. And sometimes people were kind of like a little bit, they would solve the task, but they would forget to click on, place the order. So they would solve the task, they would add to the cart, they find the right thing, but they forget to click on, place the order. And if they forget to, place the order, then our system basically says that, well, you haven't solved it, right? Because you actually haven't bought the item. And so, this is an interesting part because I think that agentic systems should be able to solve these tasks. Agentic systems should be much better at information seeking and finding sort of the information just because it requires less cognitive load, whereas people are not very good at doing that. If I look at sort of, trying to understand, where we are with these models, you can kind of like see that Llama, the older versions of Llama, they all were kind of like really bad. If I have accessibility tree plus captions, a lot of these models would kind of, go higher. And then once I have multi-modals, you have much better representation. And then once I have, the multimodal models, at that time looking Gemini Pro and GPT-4, I think GPT-4o now hit something like 90%. So like these models do climb, they do better, but they still far below what people can do. Right? Even the best models today are sitting around 20% accuracy, right? In terms of solving these tasks. And here's one example I wanted to show. It's an interesting example where the GPT model was able to successfully solve it. I ask you, I don't like the author of this image from the posts, one of the posts. Can you help me block them? And the engine would actually go, it would sort of click on the right things, it would find the post, it would go to the settings, and through sort of executing multiple clicks, it would actually block a specific user, right? Just as an example, like you give it this instruction and the model would actually go and do that. And this sort of has this notion of that I'd like to think about web agent architectures, and I'll make that reference later on for physical agents. But you can think about these sort of architectures where you observe some input, say a web page. You do some form of parsing, right, of the web page, whether it's visual and HTML or some kind of compressed representation of HTML plus visual understanding. You have an objective, right? And the objective is what I need to do. And a lot of times, what a lot of these models would do is they would generate high-level plan, right? They would generate a plan of how to execute, how you should proceed to solve the task. And then you kind of, execute the low-level actions, which is clicking on a specific element, right? And that sort of goes in loop. You can refine a high-level plan, you can execute a low-level action up until you hit a stop action, which basically means that the agent is done. I think I've solved the task. Okay. And you can think of planning as as a system. There's been some work on building these hierarchical systems where, for example, step one, I can say navigate me to a particular category, right? Step two, I want to sort based on the rating of that category, and that would be two level actions. You selecting and then you sorting, right? And then maybe you select an item under $20, and then maybe you buying a selected item, right? You need to buy it, and then it's three low level actions. You add to the cart, you proceed to the checkout, and you do shipping. So there is some sort of work right now that's trying to have the planning model that actually plans what you need to do, and then you execute those. So Visual Web Arena, we think of it as a step towards building general purpose agents, right? It's a simulator, so you can evaluate those models. Tasks that we design are not very consequential at this point. They don't really represent significant economic value at this point. And we've designed these tasks to be simpler because the current large language model agents or AI agents do not even do well on these tasks. The gap is still fairly significant. And the long-term question is, can we automate productive, economically valuable tasks, right? One of the interesting failure modes that we see these models, and again, we're fixing those. A lot of that is sort of progresses as the models become better and better. But one of the things that we're seeing is this notion of long horizon reasoning and planning, right? So models sometimes oscillate between two web pages, or sometimes they get stuck in the loop. So it's, I'm trying to do something, I go to this web page, and then I go back, and then I go forward, and I go back. So there's a notion of persistent memory. A lot of times, sort of, memory is missing. So good representation of what I've done so far is missing. Of course, I can concatenate every single web page I visited with every single HTML, but that becomes fairly cumbersome, right? You need to have a good persistent representation of the memory. A lot of times, models would correctly start on performing tasks and then undoing them. I don't know why. It just basically means they don't have very good reasoning abilities. And a lot of times, agents tend to stop exploration and execution too early. So instead of exploring what are the possibilities there, they actually try to do something, and then you stop and you basically execute the stop action and says like, I can't solve the task. I'm not seeing how I can solve the task. And there's also some failures in visual processing. So sometimes you can click on the wrong items, identifying specific items in complex web pages. There is also, they lack a little bit of spatial reasoning. Like if you're asking it the question, what are the prices of products in the first row? You kind of like have to understand what the first row is, what the second row, and like what's the middle row, right? So certain spatial, understanding is missing, but I think those things will potentially get better and better as we sort of can get the data for training these models. Right, so what we need to do a lot more to close the gap. Definitely reasoning and planning over long horizons. And that's, I'll talk a little bit about this, but that's one of the key failure modes. We also need to allow agents to search. You can think of it as executing and coordinating multiple instances in parallel and asking for clarifications and confirmations, right? So a lot of times search is actually, you can think of it as test time inference technique. It basically tries to explore possibilities to figure out what's the right way to solve the task. And asking for clarification, this is where uncertainty estimation comes in. It's also fairly challenging, where you basically, the model has to understand that it's confused, and then has to go and ask humans for clarifications or guidance. And obviously you need strong, vision language code models, and also identifying appropriate levels of abstractions for agents. Like, do you rely on screenshots, what you're seeing visually, Do you rely on HTML, or maybe you rely on APIs? A lot of, there's a lot of websites that would have APIs. So maybe instead of actually going through the web, you actually go through API calls, right? And again, I think that multimodal models here becomes very important because a lot of real world tasks will require some form of visual grounding, right? So for example, if you interacting with PowerPoint, if you're interacting with Photoshop, right? A lot of it, yes, you can do it through API, but a lot of things are also done through visual grounding and visual understanding. So we definitely need to train and build stronger vision language models. So that kind of like gives me this notion of visual web arena, which is the environment that we use for doing evaluation. Now let's talk about the research, or we can think of it as, again, test time inference. One interesting thing about agentic agents in general is that you have this notion of exponential error compounding, right? So for example, if your model is accurately can be accurate at one-step prediction at 90%, then if you're executing, 30 actions, then your accuracy goes down to 4%, right? So you basically need to be very, very accurate. So you need to be very precise in terms of like executing each step in order to be able successfully, solving long horizon tasks. And that's pretty well known in anytime you have sequential decision-making process, you have this issue, right? The errors do compound over time, which makes it a very, very difficult task. So what happens here? Well, local decisions have global consequences, right? So for example, let's say I ask you the question, add coconut milk to my cart. Well, I can click on element ID 31, or maybe, and that gives me to the next state, or maybe I can click element ID 24 that gets me to the next state, right? And then so forth. There's sort of different choices. There's a lot of actions. Like the action space could be exponential, especially if I'm doing searching as well, right? So I can type text. And so you can imagine that each one of these sort of leads to a trajectory, right? Once I execute the trajectory, then potentially I can evaluate, which one is right, which one is wrong. And let's say, basically this state gives me the right outcome and all the other states don't. And especially, if you're executing actions, 30, 40, 50 actions, that becomes very challenging. And if you have a policy right now that, you can think of VLM as your policy that basically predicts the probability 0.5, you should click on this action, and probability 0.1, you should click on this action, then obviously, finding the correct path is going to be very difficult, right? So, you basically have to be able to explore the environment very efficiently, right? In this sort of exponential, in this exponential space. Now, one of the things that turns out to work okay-ish, or at least as a first step, is doing search by repeated sampling. Right? It's a very simple idea, very easy idea. You sample action from your model until you hit the stop action. Okay, so let's say you sample this path. And then you evaluate the resulting trajectory. So you look at the trajectory and you can say, have you solved the task or did you not solve the task, right? If you have a verifiers that can tell you that you solved the task, then you know whether it's success or not success, right? And if it's a not success, then you repeat, right? This would be an instance of what's called rejection sampling, right? You generate the trajectory, you look at the outcome, and if you didn't solve it, you generate another trajectory, right? This is a very simplistic, way called rejection sampling. You basically sample until you hit the right answer. It's fairly inefficient, but it's surprising that a lot of work that's happening right now, for example, in space of reasoning, like models like O1, O3, or DeepSeek, they're essentially doing exactly this. They're essentially doing rejection sampling. I give you the math problem, I start generating thinking tokens up until I get the right answer, right? And so I start with simpler prompts. I generate, sometimes right answers, sometimes wrong answers. I use, reinforcement learning to reinforce positive and then de-reinforce negative. and sort of start scaling it up. So the simple idea of rejection sampling is essentially what's driving a lot of innovation right now in reasoning capabilities, right? Which is amazing and was very surprising to me that it actually works. So we've sort of started looking at exactly the same problem, but for us, in this particular domain, it's not that you can generate, thinking tokens and then you basically get the answer. Here, you actually have to execute actions in the environment and you change the state of the environment, right? Which makes it much more difficult. So here you do rejection sampling, and hopefully at some point you'll hit the right answer. What happens is that repeated sampling tends to help, right? So here's the number of 10 runs, and this is what we call pass at 10, which basically means that if you're running your model 10 times, one of like in terms of like you hit like 15% probability of getting the right answer, right? So the more you sample, the probability that you'll hit the right answer among these samples is kind of is increasing, and that's what this graph is showing. All right. And however, the space is exponentially large, right? So can we guide this exploration? And the key idea here is to apply the value function to intermediate nodes. It's a very old idea, but you can apply it actually in this space as well. So how does this work? So the idea is to basically do a form of a best first search algorithm with a few tweaks. So what are the ingredients of the algorithm? So the baseline agent proposes actions. The baseline agent actually says, okay, here's two actions that I can take, right? These are the most probable action according to the base model or according to your original policy. You have to have a way to backtrack in the environment, right? So that basically means in this state, you want to be able to backtrack to the original state. This is sometimes difficult to do, especially in web environments, because some actions you can't backtrack from, and these actions that we call destructive actions, like if I place the order, I can't just go back and unplace it, right? That's just one example. So we'll talk a little bit about this. And then you also have to have a value function. You can think of a value function that takes the input, whatever your representation is, plus it takes a sequence of previous observations or previous steps and outputs a score. And you can think a value function essentially looking at the expected value, expected reward. Think of it as, in our settings, think of it as the probability of successfully solving the task, right? So it's a number between 0 and 1 that basically says if I'm in this state and my value function is, 0.5, then the probability of me succeeding is 50%. And if the value function of in this state is 0.3, then the probability of me succeeding is 30%, right? So maybe this state is better than this state. So you have to have a good value function, right? And these are kind of values that you can associate. And what we've done in this work is we basically using LLM as a judge. So we, in this case, you take a GPT-4o, you take the full trace, the full trajectory, and you're asking the model to say, how good the state is in terms of solving a particular task. So there's a way to sort of, use this LLM as a judge. There's a few tricks of self-consistency that you can use, but essentially you can just use a large language model as a judge to judge each state. Ultimately, I do believe that the next generation models will create their own value functions. You'll train your own value function that basically will guide this exploration. Okay, so how does this work? Let's say that I give you a task, right? The task instruction is, can you add this and the other canned fruit of the same brand that looks like this, but red instead of brown to the comparison page, okay? So how does this work? Well, you take the action, right? And then at this point, you have three possible actions to take, right? They all have a probability, they all have a value function of 0.45, right? So you pick one of them, you proceed, and then you go to the next kind of state and your value function decreases. So you basically say, okay, maybe I'm on the wrong path to solving this task. And then I backtrack and I take another action, right? So I backtrack to the previous state and I take the other action. And let's say here I go in, my probability increases. I go in, my probability increases. and then I hit a particular state where, I'm not actually going to solve this task, right? Because, my value of the state is actually pretty small because I ended up in a very wrong state. So then I have to be able to backtrack again from this state. I have to be able to backtrack back to the original state, right? And then go and sort of, again, take the next state, and then if it's bad, backtrack and eventually solve the task, right? So you can sort of see that it's more expensive. There are different ways of exploring, but the key here that drives a lot of this exploration is the value of the state, right? Which basically is telling you how good the particular state is in terms of solving the task. And you can kind of like, spot the errors early on and say, no, 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 backtrack and restart again. So it's a little bit better than just doing random rejection sampling, because here you're doing guided exploration. It's very similar to, if some of you familiar with AlphaGo setting, right? Where you basically have an environment where you have a value of the state, and then, you try to explore which actions to take, and you sort of evaluate those states given the value function that you have. And so if we look at the results, what we found is that, for Web Arena, there is pretty decent improvement in terms of the ability to solve these tasks. For the Visual Web Arena, we also see, quite reasonable improvements by using this exploration. It's more expensive, but and so we do see that these sort of search at test time actually improves model's ability to solve the task, or at least to solve some of the tasks. You can still see that we're still very far away from hitting like 90% accuracy, right? But nonetheless, it's actually a progress where we're progressively improving. And we do sort of see that if you look at the success rate, right? C0 indicates no search. And then, the more node expansions you have, the better your performance is. And then you can also sort of look at the success rate relative to, how you want to expand. Do you control the depth versus the breadth? And sort of, again, how much you want to explore versus what's the branching factor. And then if we kind of, keep exploring and doing the branching, then the accuracy tends to go up, just because the model is able to explore possible different possibilities, like, or different environments. A lot of times what we see in sort of in these settings is that, if I ask you to buy a blue polo shirt, if you don't do the search, the model, let's say, goes and let's say it clicks on the wrong thing and it ends up on a web page that only has blue polo shirts, right? So you're asking black polo shirt and it gives you blue polo shirts. And then the model says, well, there are no black polo shirts because I'm only seeing blue polo shirts. I can't solve the task. Done, right? And obviously, this is the case that if you can backtrack and sort of explore, you will find the right answer, right? So this notion of search is actually becomes fairly important, right? And such. And we also found that having a good value function is essential, right? There is still a lot of headroom for improving the base policy. Obviously, your base policy has to be good. It can't just take random actions. If your base model is actually pretty weak, then you'll just be taking random actions, and there's only that much you can do with exploration. But you sort of need to improve both, right? And you can kind of like see if you use different value functions, then the performance is actually improved. Like with no search, if you sort of like say Lava, which is a weaker version, you get the improvement. If you use something, for all type of models, then, you have, so if you have a better value function, kind of like looks at the full trajectory, then you have improvements in performance. And the interesting thing is that using LLM as a judging whether the trajectory is good or bad is much easier than predicting what the next action you should take, right? Or what the next sort of element you should click on, what you should be searching on. And so that's why sort of, starting using value function as an LLM initially, I think it's a reasonable thing to do, but obviously you want to be able to improve this. Here's just some examples, right? You can basically say, I recall seeing this exact item on the site. Help me find the most recent post of it. I recall seeing it in either collectibles or in tick section, right? So the models would kind of like go the starting state, it would sort of explore and then eventually find that particular posting, right? Or this one where I can say, hey, I like this. I need something like this in my apartment. Can you add one? Can you add one to my wish list? So the model kind of like have to go, it has to sort of like search through different environments, find this specific item and add it to your wish list, right? It would be great if you have something like that, right? You take a picture of something and you basically tell your agent, hey, go and find it on Amazon, Best Buy, wherever. Get me the best price for this, right? And you know, see where I can buy it. Just as an example. Now, in terms of limitations of this, well, search is pretty slow, right? So you obviously need a fast way of doing backtracking. We sort of did the backtracking in a relatively naive way. You store all actions in a queue and then take them again to get to the original state, right? So if you're taking 20 kind of like actions, you store what you've done so far, and then to go back, you rerun that again. So it's not very efficient what we've done. I think it just requires sort of like infrastructure work. And the other interesting piece is dealing with destructive actions, right? Certain things on the web are very difficult to undo, especially if you're operating on the real web for testing these models. You can't order the item and then unorder it, right? It's not like you can order the item and then your model says, you know what, that was actually the wrong order. Let's try ordering something else. You can't do that, right? And so the other thing that you can't unfortunately do in the real web is it's very hard to do some form of learning in the real web because anything that changes the state of the environment is actually fairly difficult, right? I can't go on United and start booking flights from Pittsburgh to San Francisco to learn how to book the flights, right? Because if I'm sort of like exploring and I'm kind of like saying, why don't I click here? Well, maybe I should click here and then maybe I should kind of like try to book this flight and then maybe it's wrong and try to book this other flight. And so it becomes a little bit tricky to do because essentially United will block you or United will basically say, oh, there's so many people are trying to book flights from Pittsburgh to San Francisco. Maybe we should like increase the prices, right? So you have to be careful how you're actually operating in the real world. So what's the current work? Obviously, search as a policy improvement function. You can use search as a way of finding the correct trace or the correct trajectory. And you can use this potentially in either in reinforcement type of learning algorithm or actually in SFT to try to, um, um, fine tune on this. Improving value function by fine tuning instead of prompting. So if if you can improve the value function by using Monte Carlo rollouts, you can do that. Obviously exploring trade-off between improving baseline agent, how much your base model has to be versus how much more search you have to do at inference time, right? And today we sort of see this notion of test time inference, scaling loss, where well, if I do search for more, I can probably get a better answer. And I think that it's true, but it's sort of both models need to improve, right? Your base model needs to be better, and also search needs to be more efficient. And obviously, one of the biggest questions, if we don't have a simulator of the web environment, right, how can we collect data at scale? And that's one of the interesting problems that we also started looking at. What can we do and how we can collect the data at scale? Because the interesting thing about agentic models in general is that it's the kind of data that's very difficult to find on the web, right? Like, so what we see with existing LLMs is that, I can crawl the web, I can scrape images and HTML, and then I can pre-train these models just doing the next token prediction, right? For agentic work, it's very difficult, right? It's very difficult for me to say, hey, give me a whole bunch of examples and show me how I should be booking my flight from Pittsburgh to San Francisco. All right, or show me in this setting, I hey, I like something like this, add me to my wish list, right? It's not like you can find a lot of these examples on the web and of examples of people showing you how to solve these tasks, right? So this notion of giving the task and the full trajectory of how you should take actions and solve the task is actually very limited data that we have today, right? In fact, we don't have any of that data. A lot of companies, they essentially collecting this data in-house by asking people to, solve these tasks and do like massive massive annotations. So the question for us was, how can we collect the data at scale? And that gives me to the third point, which is how can we at least try thinking about what we can do here. So as I've mentioned before, agents suffer from a data problem, right? And you can see the gap is still pretty big. And when we think about LLMs, the way that we're training them today, a lot of times they often trained online. I just collect a bunch of data. And then I deploy them as zero shots as agents, right? And then, I collect a lot of data. I do some form of supervised fine tuning. At least that's what's happening in academia. And then, I try to deploy them and see how they work, right? The question is, can we somehow go on the real web and generate synthetic tasks to unlock this large-scale training of agents? Okay, and the question is, how can we again get these models to generate something synthetic and actually, build something that we can train on and improve our agents without human intervention, or without actually, task generated by humans, because it's fairly expensive to ask humans to generate or create those tasks. So one of the things that we've been trying to build is we've been trying to build this internet scale training for agents that we call Insta, which is, the idea here is we're using llama models to generate and verify synthetic agentic tasks. So we're thinking about three stages, right? There is a task generation stage, right? For example, I can ask the model to say, find me a code base for generating images with Flux 0.1, right? That's the first task. I'll show you examples of how we can do that. The second task is evaluation, actually executing this task and then trying to see whether, the model solved the task. And then the third step is actually basically collecting it at scale. But you can think of this environment is that the model proposes tasks, the model executes those tasks, the model then evaluates those tasks. And then, if it successfully says, yeah, I proposed the task, I executed this task on the real web, I evaluated, I think I've solved the task, then that becomes a very useful data for training our agents. Okay, so let's see how we can do. So for example, given the web domain, for example, there's a domain, just random domain, Mercy Ferries. It's a website in the UK. And we can ask the system to propose realistic task that an average user could complete in one session. So there's a certain system prompt that we're asking the model to generate the task. And what's interesting that if you look at Llama 70B 3.1, I think we're also training on Llama 3.3, which is actually better, has better results. So these models, continue improving. So if I ask the model to describe what is this website about, it's actually pretty good. It sort of says, well, this particular website is official website for famous Mersey ferry service in Liverpool, England, and so forth. Certain things you can do, you can plan a journey, you can book tickets and sort of gives you ideas of what you can do with this website. And so that gave us this notion of, if the model understands what this website is about, maybe I can ask it to actually generate the task. And what we found is that, we can scale it across many, many different websites from Common Crawl. I think we started with about 1 million websites, and we started thinking about what kind of tasks these models can generate. And a lot of tasks actually involve some form of information retrieval, some sort of search. You're finding the right ticket information, you're finding booking, opening hours, you find sort of specific information on, a particular topic, right? But crucially, we do not modify the state of the internet. So that was one of the settings for us, where we asking the model to come up with a task that don't modify the state of the environment. So for example, booking something we can do, or clicking on something that actually changes the state of the environment, we can do. This specifically was done, to avoid any sort of complications of us being blocked. And as I mentioned before, we can't go on, united.com or booking.com and start running a lot of tasks, like booking a lot of hotels randomly, right? So we can only navigate to these websites, but we actually cannot change the state of the environment. What we found is that a lot of tasks that the models actually come up with are diverse, and many require multiple steps of reasoning, right? So for example, if I go to fonts.adobe.com, some of the generated tasks is browse fonts suitable for a children's book. So you have to understand like what makes a font suitable for a children's book, right? A lot of tasks can identify facts that's likely to contain. So for example, if I'm going to ancient-symbols.com, the generated task would be look up the meaning of the word OM symbol in ancient cultures, right? So if you kind of like, you have to go on this website, this is the task, and I have to crawl through this website to actually find what's the meaning of that particular symbol. Or I can sort of, go to this particular obscure Scottish design studio and ask view the latest fabric designs by this particular studio, right? So I end up on this website and I have to find the latest designs, fabric designs. And this is kind of like how it looks like. I actually have to end up on this particular web page because that lists the latest fabric designs by that particular studio, right? So these tasks are grounded even for sites in the tail of the data distributions, right? So these are kind of like, we wanted to go for breadth, not necessarily to kind of, only cover, 100 most commonly visited websites, but also going to these sort of, which gives us the diversity of the environments and different websites and different generated tasks. Okay. So that's kind of, the first step, trying to generate the tasks, right? Now, the second state is, okay, how do we know when these tasks are solved, right? And that gives us the task evaluation part. And the way we do this is we basically say, okay, if we given the task, generate a task, we can execute this task using the current model. Let's say you have a GPT model or you have your Llama model. In this case, it was a Llama model that we're using. You observe a sequence of actions and the last observation, and you now estimate the probability of a task being successful, right? So you're basically asking the model, given the last state and a sequence of actions, you're asking it to estimate the probability of the success. This is, again, the same idea as using large language model as a judge. Here we're actually evaluating the full trajectory, but you can think of it as, in the previous part when we were looking at the search, we're using the same piece, but only evaluating partial trajectories to try to figure out like what we should explore and what we shouldn't explore. Here, we're actually trying to evaluate the full trajectory, but obviously you can combine search with this technique as well. So you can kind of search around and sort of try to find the best outcome. And you prompt Llama to rate the confidence of the task that's solved, from 0 to 1. And what we found is that for example, out of 150,000 tasks, about 15% are rated a success with high confidence by Llama, roughly 22,000 tasks. We actually did verify, how good using Llama as a judge, and I think that in terms of the success, it was about 90%, right? So, for example, when the model says, "I'm pretty sure I've solved the task," with human evaluations, we're seeing close to 90% accuracy among those ones. It basically means whenever Llama says, yes, I've solved the task, 90% of the time it actually solved the task, 10% of the time, no, it didn't solve the task. So, these verifiers are not perfect, but they're pretty decent in terms of approximately telling you whether you solved the task or not. Right? So that kind of like gives you this notion of showing that you've successfully found the task, executed, and then verified it. Let me give you sort of visual representation of what that looks like. So, on a different project, we have a project where we're working with ecologists on sort of identifying invasive plants in different environments. And we basically thought, well, okay, let's look at this website, invasive plants, atlas and prompt the model to generate a task and see if the model can solve the task. So the model basically generates a task, find invasive plant species native to North America. Okay, so that's more like information extraction. And the agent response is to find an invasive plant species in North America. I will first click on link all species to view the list of all species. Okay, so it takes and based on this information, it clicks on all species, right? And that's what the action looks like. It's a little JSON that you have an action key click, you have an action, arguments that can go in, and you have a target element ID, the ID that you associated with that particular click. Then it basically says to find invasive plant species native to North America, I will first click on the link home, and because it's trying to go to the sources. And it sort of misses the point because, there is sources here, right? But it's actually insists on going home and then to find the sources. So it's sort of misread, so it made a mistake in this case, right? Since the link to sources is not on the current web page, but it is, so it's making a mistake, I will first click on the home and go back to the main page. So it goes back to the main page, and then it sort of identifies the sources, right? So it kind of, clicks on the sources. It actually gets to the right piece. To find invasive plants native to North America, I will first click on A under the native range taxonomic references. So it sort of execute pieces, and it does, clicks on the correct element. And then once it gets to the correct element, it then basically says I need to sort based on U.S. Plants that are native to the U.S. Gets it in the JSON format, and then gives you the answer, right? Since the list is already sorted by US nativity, by ascending order, that's it. I can find there's the first 165 plant species that are native to North America, right? So this gives you the list. And the answer is basically I give you the web page and I tell you the first 165 plant species on the list, invasive plant species native to North America, right? So in terms of me finding information seeking, again, this was completely synthetically generated task where the model proposed the task. It's now executed the task, even though it made a mistake. And then it gave you the action. And in this case, despite sort of reasoning, some of the reasoning failures, because it clicked on the wrong thing, but then it recovered, it found the target information. And in this case, Llama Verify evaluates this trajectory successful with confidence 1, right? And again, whenever it does this verification, it's about 90% accurate, maybe close to maybe 85, 90% accurate when we sort of did the studies, human studies. So that sort of gives you, an interesting synthetic generation, right? Where you're proposing the task, you executing this task, and then you verifying, did you solve the task or not? And again, only 14% or 15% of the tasks that the model proposes and executes, only 15% of them, the model basically says, yes, I think I solved the task. 85% of them, you can't solve the task, right? So, but that's okay because it's all done automatically. There is no human in the loop here. Let me show you some examples, other examples of what the model does. So here's the example, find me the opening hours of La Sagrada de Familia, right? It's a fairly famous church in Barcelona. So it sort of, proposes the task, it browses the web, it finds the answer, right? So, so again, this is the task that it proposes. It goes to the website. It actually finds, La Sagrada Familia. It clicks, it finds, and it basically from the table finds what the right answer is. We'll find the information on the European Union's climate action policies. So it goes to European Union Commission. It crawls the web, and then, this is a success where it actually finds the documents related to the climate action progress or climate action policies, right? And again, these tasks are completely created by model proposing what the task should be, model executing this task, and then the model verifying whether it successfully computed the task or not, right? So we sort of went through these two stages. And again, I'm not saying that that's a perfect setting. I think that, if you incorporate search, if you have better models, and then you sort of, iterate it multiple times, I think the quality of generation of these tasks could improve substantially. So let me talk a little bit about the data collection, right? So what happens with the data collection? Now we can scale up the data collection. So we've used Common Crawl PageRank to find the most important websites. We start with the top 1 million web pages. We filtered it down to about 150,000 live websites by filtering harmful content. So we're prompting the model. So if we think that there is a harmful content on the website, we basically ignore it. So we're about 97%, actually pretty high in terms of detecting and filtering harmful content. This is using llama models. We about 89% success rate in generating feasible tasks, and about 80, so it's like 90% in generating feasible tasks, which basically means that when we're verifying whether the task is successful or not, we 89%. And 82% accuracy in judging successful task completion. Sorry, that's the one where 82% whether the task is successfully completed or not. And again, we sort of went through 150,000 live websites, and then we, attempting it and verifying it, and sort of, creating data based on whether we successfully generate the task and whether we successfully execute it and then verified success. What's interesting is that we found that on sort of toyish examples and small examples, Mind to web links, these are sort of some of the data sets that people use. We found that training on synthetic and human demonstrations scale faster than just training on human demonstrations, right? So actually, if you're mixing what humans collected versus if you're mixing synthetic and humans, we can sort of see improvements. We also see that adding synthetic data improves step accuracy by, certain numbers. So that's good. We also found that if you only use human annotations do struggle with generalization. Because a lot of times what actually ends up happening is that with human annotations are typically done on a small subset of highly visited, websites. And the ability to generalize to, the tail of the distribution, that's where synthetic data really helps us, because it can help us generalize to the tail of the distribution, right? Where it's very difficult for humans to collect the data. Obviously, the ultimate choice would be to get humans to annotate the entire web. That would be the best, because then we can just do imitation learning. But we do find that sort of, the ability to crawl the web and look at the tail distribution, we do see improvements in generalization. Now, there are 385 million unique domains, right? Suggesting maybe another 1,000x more data that could be available by scaling further, right? We were constrained by compute and academic resources when we did this work. And of course, there is also sort of this notion of moving towards online reinforcement learning. So you can think about settings where you sort of run this procedure, right? You collect the synthetic data, and then you update the model and do it again. So you can sort of like, do it in online fashion, right? You crawl the web, you generate these tasks, you try to solve some of these tasks, you update the model parameters and do that again. So if you have an online, and that could be an online reinforcement learning, but done at scale, at the internet scale, I think these models would improve significantly. And of course, it's very difficult to do that on the real web because it's very hard to, change, you can't change the state of the environment. So you have to be careful how you actually scaling it up when you go to the real world or the real web. Okay. Let me just in the last 10 minutes, and I'll leave the room for questions. I wanted to sort of point out that this notion of agentic environment is also applicable to the physical agents or robots in general, right? So we've also kind of like very parallel effort. We basically thought, okay, these AI agents sort of have the same notion, whether we're operating on the web and taking actions on the web, or whether we actually have a physical agent, like a robot that takes actions in the real world, right? So for example, you can think about you observing the data, which could be the image plus maybe the depths. You do some form of semantic segmentation to understand the environment. You have an objective, you generate a high-level plan, and then you generate the low-level actions, like interacting with the actual environment. So we have this work on planning, learning, what we call plan, sequence, and learn, where the idea is large language model basically gives you a sequence of high-level plan, what you need to do. You have a sequencing or parsing module that basically understands the environment, sequences is, and then we have a low-level action, which we learn with reinforcement learning, which the little policy that actually learns how to take a particular action, right? So very much in flavor, very similar to what the web agents are doing, but now we're actually interacting in the real world. So for example, a planning module can say, okay, here's the task, get me, I'm trying to kind of like put the silver nut in the silver bag and the gold nut in the gold bag, and then give me the simple plan to solve this task. And so the LLM basically produces a fairly simple task of how I should solve it. We have a sequencing model, which looks at the observation. There's a depth. We do segmentation and sort of a little bit of projection, so kind of like have some form of 3D representation of the environment. And then it goes through the inverse kinematic, and we have a motion planner. But you can think of this as sort of like, again, understanding the environment and doing a little bit of motion planning. And then the low-level action module actually learns the local policy, right? So here you have reinforcement learning for interactions. You're kind of like locally learning how to interact with it. Much like when you're clicking on a particular element, here we're actually learning how to, control our joint angles so that we can accomplish a low level task, right? And so this is how it sort of looks like, where a local model is actually learning how to, with reinforcement learning, it's actually learning how to interact with the environment. And so kind of like in the full pipeline, very much in similar spirit, you have a planning model that plans, gives you high level plan. For each high level plan, you executing this lower level actions where you basically have pose estimation, motion planning, a little bit of reinforcement learning to take the action. And then, you have this low level control that actually controls low level actions via reinforcement learning, right? And then you proceed. And that's just the first step. And you go to the next, and then you go to the next and sort of execute that according to the plan, and so forth. And we found that these sort of models, work reasonably well. PSL solves about 25 long horizon robotic tasks across, in this case, 4 benchmarks, with, about 85% success rate. We also tried extending this to the actual real environment. So here's I give it a task, put mouse in the drawer. So the model basically generates the plan. And again, it looks at the environment, parses the environment, and then executes lower level actions, right? And it sort of does a lot of interesting things. It can, but the point I do want to make here is that whether you're operating in the virtual space or whether you're operating in the real world space, the ideas are fairly similar across domain. And so here you can generalize to new object geometries, new categories. And so we've never trained on this particular for this particular object, but you can sort of successfully complete it. You can deal with multiple novel objects with unseen receptacles. So, these models can do, reasonably well. It's not perfect by all means. I think we're hitting success rates of about like 80 to 90%. But these models do generalize. They can manipulate deformable objects. You don't observe them when we were training these models in the simulator, but training in the simulator does translate into the real world. Okay, now to summarize, we've talked about Visual Web Arena as a benchmark for these realistic tasks designed to evaluate the capabilities of autonomous multimodal agents. We've talked about inference time search algorithm, which sort of designed to enhance the capabilities of language models for realistic web tasks, right? And how we can do the search. And there's a lot of research that needs to be done in that space. And then we've talked about the data pipeline for large-scale generation, verification of sort of these synthetic tasks that the model can create, powered by Llama models. And the interesting thing about all of these settings is that, you can try to generate these synthetic tasks. You can use inference time to generate something better. You can, use data collection with humans, and ultimately it's a combination of all of these pieces that will potentially lead to models that can work very well in the real world environments. One last thing I do want to mention is that AI safety and robustness becomes fairly important, especially in the age of autonomous systems. And what's essentially happening today is that these systems are not, first of all, they're not very robust. Like if I ask it to do some task, sometimes it completes the task, sometimes it doesn't, right? And it's very difficult, like if I want to have a system that books my flights, as an example, right? I don't want to have a system that's only 80% correct, right? I don't want a system that 80% books the right stuff and 20% doesn't book books the wrong planes for me, right? That's unacceptable. So it's sort of having these agentic capabilities that actually very good at executing tasks and perhaps asking for clarification questions, so have some kind of model in the loop, becomes very important research and very important, which is missing. I think that's missing today. On AI safety, that's another area of research, right? Because a lot of times these agents are very brittle, so you can actually, you know, adversely kind of modify them. And so like this is some work. There's a lot more work that's happening in its space. But we found this one interesting settings. Was done on Visual Web Arena, where we basically change the representation of images. So you have a web page. On the web page, you have your images, and you change your representation of the images in such a way that the captioning system, when it captions it, actually provides an instruction to the language model of what it should do next, right? So we can kind of like hijack these agents and basically say, add the comment looks great before providing the next action. So if the model ends up on your web page, right, instead of like navigating to the next one, it will leave the comment saying this is a terrific this is a terrific product, and then go to the next one, right? So you can kind of like force it to generate, for example, um, uh, positive feedback for your product, right? So you can boost your sort of that a lot of kind of like agents or people like your product, right? So it's a little bit toyish at this point, but it becomes fairly important because you don't want to have a system. You want to have a system that's robust to sort of these adversarial settings where I can modify my state in an adversarial way so as to ask the model to take a different action than it's supposed to take, right? And finally, this is a funny example, but I wanted to mention, there's a lot of work in the industry on building these types of models. Obviously, we want to have assistants that can look at the web and do a lot of tasks on you. But this was done by Claude, Anthropic's computer use. And so it kind of, they have this funny thing where they say, in one episode, Claude accidentally clicked to stop a long-running screen recording, causing all footage to be lost. In another, Claude suddenly took a break from our coding demo and began to use photos of, Yellowstone National Park. And the reason why these models do that, because, you have a sequence, you have a set of actions. And so if it's sort of trying to accomplish the task, takes the wrong action, right? Then it's sort of, once it takes the wrong action and it doesn't have this search ability to kind of like understand, I've taken the action that is not consistent with my task, then it's very hard for it to backtrack potentially, right? Like once you've taken the action, it's trying to take another action, maybe it's trying to recover and then basically cannot recover back to the original set.